everyone, welcome to the next session on ANSYS Workbench tutorials. In this session, we are going to analyze the tibia bone for its modal analysis. This is the tibia bone which you can see. This is also called as the shin bone. This is something which is existing between your ankle and the knee. So we are going to analyze this bone for its modal analysis. At this end, we are going to fix it, and then we will see what are the various modes of vibration of this bone. We will start by double clicking on modal module. Next, we will go to engineering data. Tibia bone is not going to be there as a material, so we need to enter its properties. These are the properties which I have used for the femur bone analysis. The same properties I'm going to use because we are considering the same person for analysis and its bone density is not going to change. So we will take up this value of density. It is 2000 gram per centimeter cube. Next, we will give isotropic elasticity. The value is 2.13 E9, and the value of Poisson's ratio is 0.3. So these are the three values. Now I'll go to project and update project. Next, I'll go to geometry and I'm going to directly import the geometry which I have with me. I'll give you the link for the geometry so that you can download and use it for your analysis. Next, we'll go to model and double click on it. We'll first go to geometry and change the material to the one that we have created. Next, I'll go to mesh and I'll change the sizing to fine. Now, in this version of ANSYS that I'm using, 18.1, I can change the relevant center from coarse to fine. In case you're using a higher version where this option is not available, what you can do is you can give the element size. Say it is 0.01 mm or 0.001 mm. Now, it depends on your processor as well. If you have a good processor, then you will be able to get the meshing very fast. But if your processor is not very fast, in that case, you will find it very difficult to mesh. So accordingly, choose your mesh size so that your PC doesn't get hang for longer duration of time. Now I'll go to update. Once this is done, I will go to model A5 and I'll insert fixed support. At the bottom end. Next, I'll go to solution and solve. Once you solve it, you will get these red lines over here. This indicates that six natural frequencies of this bone has been generated. If you want, you can increase the number of modes by clicking on analysis settings. You can see here max modes to find. It is 6 by default. You can either reduce it or you can increase it based on the requirement of your modes. So now I have given say 10 of it. So I'll just go to solution once again and solve. You can now see that initially there were 6 lines over here. It has now increased to 10 of them. And in this table, you will find that there are 10 natural frequencies obtained. Once this is done, I also want to know that for each mode, what is the value of deformation which is induced in the bone. So I will click over here, right click, select all, right click, create mode shape results. You can see all the deformations have been obtained. So I'll just go to solution and solve once again. Now once you solve, you will get the deformation corresponding to each mode, and also the frequencies for that mode have been obtained. So once I go to the first deformation, I can see that the maximum deformation that will be obtained is 1.898 mm, and the frequency is 0.52 hertz. It is a very small value. So you can just animate and check what would be the motion in that bone if this natural frequency is tapped. Now we'll go to the second deformation. You can see the value of deformation obtained is 1.86 mm. The frequency at this point is 0.61403 hertz. This is the second mode that we are analyzing. You can animate and check this result. Next, we'll go for the third mode. You can see here the deformation maximum value is 2.6678 mm, and the frequency is 4.5311 hertz. You can again animate and see this result. The maximum deformation is 3.0048 mm. This is the deformation highest value, and the frequency is 5.3226 hertz. You can again animate and see this one. The animation is important because if this natural frequency of the bone is tapped, it is possible that your bone may start vibrating with this motion. Next is the mode 5, for which the maximum deformation is 2.25 mm and the frequency is 6.1937 hertz. You can again check this animation. Next is the mode 6, for which the maximum deformation is 2.5097 mm and the frequency value is 14.383. You can see that there is a significant change in frequency from the fifth to the sixth one. The fifth was 3.19 hertz and the sixth one is 14.38. There is a significant difference of value between the two. You can animate and see this result. Next is mode 7, for which the maximum deformation will be 1.8411 mm and the frequency is 15.708 hertz. You can animate and check this. The next one is mode 8, for which the deformation value is 2.5687 mm and the frequency is 19.237. Now again, between the 7th and the 8th mode, there is a change of frequency that you can see, and there is a difference of a certain value. It is not as much compared to the 5th to 6th transition, but it is a good difference that you can see here. You can animate and see this result as well. Next is mode 9, for which the maximum deformation is 2.9 mm and the frequency is 28.176 hertz. You can see a significant difference between the 8th and the 9th mode. You can again animate and see this. And for the last mode that we have chosen, the maximum deformation is 2.9688 mm and the frequency is 36.219 hertz. You can again see a significant difference between the 9th and the 10th mode. You can animate and see the result. You can observe one thing, that the deformation value has not changed significantly. It is almost the same. It is a range from 2 to 2.5 to maximum 3 at certain cases, but it is in the same zone. So the deformation is not the concern here. The concern is the value of frequency, which has to be analyzed, and it has to be maintained such that this value of natural frequency is not tapped. Otherwise, the bone may go into this kind of vibration. Now, you would wonder that this frequency is something which we encounter on a daily basis. Then how come the bone doesn't move so vibrantly? Then it is because of the bone which is beside it. There is a fibula bone which is attached to it, and this is another bone which keeps it in place. Also, we have analyzed the femur bone in the previous sessions. So, accordingly, there is a femur bone also above this bone, and there is a knee joint here, a kneecap, which holds these bones in place. So, because of this, we are able to walk, we are able to run, we are able to sit and stand. But even if we encounter these frequencies, the bone remains safe. But it is always crucial to take care of these bones in the cases where you are going for, say, some fracture analysis, or maybe you are fixing some bone plates on it in case of some fracture, or maybe there is a kneecap defect because of which this bone is not in position, or there could be some ligament tear at the top and the bottom end where there is some cartilage, as you know. So, if there is a defect in those cartilages also, then this bone becomes weaker and subjected to these kind of vibrations. And when you encounter these vibrations in such situation, it is possible that the bone becomes weaker and it could undergo some kind of an accident. So it is very crucial to know these frequencies, and hence you can use them in your biomedical applications. So with this, I end the session. I hope you have understood the analysis. If you have any doubts, please write to me in the comment section. Don't forget to like, share and subscribe to the channel. Hit the bell icon for latest video updates. See you in the next session. Thank you.